even with the answers, I was still confused.
Ruth, why are we laughing about that?
I was struggling.
I guess it's a laugh so you don't cry.
Yeah.
Okay, fine.
I had enough crying today. I need to laugh.
Okay,
I love this space.
so we are in that third note packet now. Oh, what is this? Oh, it's Charlotte's homework from before that I'm supposed to be grading. I'll do that later. Everyone. We're just missing 3. Marina's probably not allowed to go home. I mean, they're certainly not going to go home, but she'll probably not leave. She probably can't leave campus.
Yeah.
This is just the 3 of them, or are we missing more? No, Daniel too. Or 4 of the 9 of you. It's awkward. That's fine. Well, it's not like we're doing the hardest thing we've ever done. We are. This is it now, yeah. The function proofs are real messy, and students struggle with them in classes that follow this one.
Thank goodness. Oh, seriously? Thanks.
You guys should be really with it.
Thanks.
Your things in number theory and abstract algebra, real analysis, these proofs are the thing that are going to be difficult. Maybe they're not the thing, but anyway, this is the trippiest of all the things we've done so far, I think. But because like we know what an even number is and we know what a rational number is, and like doing stuff with those is not that different. Like we also know what functions are, but do we really? So anyway, we're gonna do this.
I just kind of know, okay, that's a function. Nobody really defines what a function is. Like, oh, okay.
You don't know what a function is?
I know what a function is. It's just
It's a mapping. The what? No, what? Tell me what.
They just said, oh yeah, that's a function. Okay, so I'm like, okay, f of x is this thing that's after the equal sign.
Oof, that's before anyway.
F of x is no f of x
Is equal to that stuff.
something,
Okay.
and I know that something is a function. Okay.
If I see f of x function.
Right. It's a function whose name is f and who the input value is x. Yeah. It's a mapping from one set into another. Let's talk about what the sets are here.
Oh, yeah. Got you.
So on the function f of x equals x squared plus 1, what is our domain? What types of numbers are we plugging in there? What does that mean? Is it just integers?
Well, you can plug in any number.
What kind of number? A real number, yes. These are real numbers. Those are any type of number is a real number, right? You don't mean a complex number because we probably shouldn't. Yeah. No, okay.
Okay.
The domain is the real numbers. What is the target? So the codomain. And I don't mean the actual, like I mean types of numbers. What are we mapping into?
Real number?
Also the real numbers. Good. This function exists in the XY plane. It's a good I'm gonna call these do and codo. Cool. No, then you don't do it. Okay, so we have the domain, the codomain here. What is the actual range or the image for f? The image, the things that are actually getting mapped to. What does x squared plus 1 look like?
It's So x squared is a parabola plus one, so it's shifted.
So what's the range? What numbers actually get mapped to?
One, two, eight.
It is facing the other way. This is a upward opening parabola.
Oh, right, okay.
It starts at one and goes on forever.
I slid.
What are we plugging in on this other one? F of x, y is x squared plus y squared. What does our input look like?
Real numbers?
Two real numbers that are grouped as an ordered pair. And what did we learn? That is
Cartesian product?
the Cartesian product. This is R cross R. The domain for this one is R cross R. Taking an ordered pair of real numbers. Okay, so the domain is R cross R, and what are we mapping into? What kind of number?
Real numbers?
Is it the same thing or is it R? Because R cross R and R are not the same. So
Cartesian products.
is it a Cartesian product? Is the answer an ordered pair? It's not, y'all. What's 2 squared plus 0 squared? That's just 4. It's not an ordered pair, right?
Oh, so it's just real
Just
numbers.
Oh, right.
Right,
Yeah.
right. This is just the real numbers. Yeah, these were
Yikes.
supposed to be easy examples. Okay, so the domain is R cross R, the codomain is the real numbers. What is the image itself? The range or the image, what is it? What types of actual numbers do we get back?
Real numbers?
Which ones? That is correct, Whitney. I did not appreciate the question mark, but that's correct. Okay, we are gonna do the same thing for these functions down here. So two functions are equal or equivalent if they have the same domain, codomain, and mapping. So the function looks the same, the domain and the codomain are the same. Do you have your hand up, Logan? No,
No,
okay,
not much.
okay. So with only like 6 of us here, we can just talk to each other. You don't have to raise your hand, okay? Okay. So maybe even if there were 10 of us, it'd be fine. If you just talked. I'm talking in Zoom, I hope. Did I share my screen? Surely. Okay, so we have function f from R to R is defined by f of x equals x squared. We're gonna give the domain, codomain, and the image or the range. What is the domain? It's sitting there looking at y'all. It's the real numbers. What is the codomain? Also sitting there looking at you. Good, it's the real numbers. What is the range or the image? Good. 0 to infinity. Any questions, comments? No? Feeling good?
Feeling good.
Okay, we're managing.
Yeah, we're just managing.
On number 2, we have this function g from the reals to the non-negative real numbers defined by g of x equals x squared. We can give the domain, codomain, and the image. What's the domain of g? The real numbers. What is the codomain? Nope. Yeah, it's the thing looking at you. The map is defined from this set to this set, right? Ruth, look, that tells you it's going, this set is the domain, this set is the codomain, always. Okay. What is the range or the image or the things that are actually mapped to? Our f and g equivalent functions. No, why?
They don't have the same, domain.
Good. So something about these two functions that we'll talk about in a little while is that that first one is not onto or surjective, and the second one is. A function being onto or surjective is really helpful. And so the first one isn't, and so it's a whole different category of function than the second one is, even though they look the same, right? The fact that their codomains are different matters. Bless you. Okay. So the identity function from X to X, it just takes everything to it. So that's not hard. Yeah. Under the identity map, nothing happens. You just get back the thing you started with. All right, bless you again, but that's the last time.
No.
Okay, so we have our definition number 3. F from X to Y. Now remember, y'all, that notation is this function F from a domain to a codomain. So the domain here is X, codomain is Y. Is a function. We're gonna let A be a subset of X and C be a subset of Y. The image of A is f of A, which is equal to the set of all Y in Y, where there exists an X and A, where Y equals f of X. Like I said, that's a lot of words, letters, things, symbols that mathematically look hard, but are not that hard. The image under this set, under the function f of the set A is just all the crap that A maps to, right? Everything, every element in A goes somewhere. The collection of all of those somewheres is f of A. Yeah? Okay, so it's the stuff in Y that got mapped to by something in A. So if we are looking at like a picture of this. This is A, this is your domain X, your codomain Y. This little set here is f of A. Wow, I don't know why I made that where I couldn't write in there. This is my choice, how big this thing is. So like, I like to use darts for my explanation of set stuff. So I have y'all are just gonna imagine this with me, that I have a dartboard on this door over here, right? And I have a collection of darts in my hand, that's A, yeah? And I'm gonna just toss them all at the dartboard. They're all gonna land on the dartboard. Yeah, pretty impressive. On this dartboard, the collection of all of those spots, the target, where they all landed, that's f of A, that's the image of our set A. Okay, so it's all of the somethings that I hit with a dart from my set A.
So the second circle is f of A inside the little.
Under this function f, yep.
Oh.
Okay, so the inverse image, that's the pre-image, so we're going the other way. And I mean, the inverse image sort of tells you that, or you think the pre-image also sort of does, I guess. So you have this, let's see. You have this set Y, your codomain Y, and there is a set C in it. And this set, the pre-image of that set is a set in X. So this is F inverse of C. You can think about this as the collection of objects from X that under the regular map, mapped into C. So when you undo it, they came from C. stuff in X. Sorry. So like a takeaway or something to like make note of here is that f of A is a subset of your codomain, and f inverse of C is a subset of your domain. Like it's uncomfortable maybe to think about these things and like where the sets actually are. Like A is in X, but f of A is in Y. C is in Y, but f inverse of C is this thing in X. So I think pictures are gonna be important here until we can sort of like get really comfortable with the sets where they are, or whatever. It makes sense why we just did a bunch of set theory stuff and set operations, subset stuff, because now we are using them with functions moving from a set to another set. All right, so we have these on number 2 here. We have U and V are subsets of a set A. U is contained in V. So U is contained in V, V is contained in A. We're good there? Yes? They're both subsets of A. So let's say this is A. Whoa, okay. That's our set V and our set U. Okay, thanks, Notability. So you have this U and V are subsets of A, U is contained in V. Then their images, that image is preserved under this function. Or the subset stuff is preserved under the function. So what that means is that when we map this over under F, the same kind of thing is true, that we get this F of U set, and that is fully contained in the F of V set. So one of the things about these proofs, again, like knowing where you are and what you're trying to do is important. So we get to assume when we do this, we didn't count Kaylee too. That's more than half. Or is it actually half? Yeah. Wow. Okay. It's just half. U, V, B subsets of A, and U is a subset of V. What we are trying to show, what we want to show is that F of U is a subset of F of V. So I don't really care about anything else right now. I'm trying to show this subset, that this is a subset of this. So how do I do a subset proof?
Pick an arbitrary element and you would try to prove that it's also in V.
Okay, so where is F of U? Well, we haven't really talked about this, but I guess we have this F, we can say is a function going from X to Y. So like really you have this bigger set X and this bigger set Y. Okay, so where is F of U? My pointer thing is not working today for some reason, which is super duper irritating. Wait, will this work? What does this do? No, that's not helpful. Nope, still nothing. Nope. Good. Okay. F of U is over here, right? Which is in our codomain. Yeah. So to help me keep track that that is the codomain, I'm gonna let Y be an element in F of U, right? The idea here that what I'm trying to do is to show that this is a subset of this, so I need to pick an element in here, arbitrary, and show it's in here, right? Yeah. So I'm gonna pick this arbitrary Y in F of U. Now, what does it mean for an element to be in F of U? Go back up to the top of your page. So there exists an X in U where f of X equals Y. Right, if you go back to the definition, I cannot scroll. Being in f of A is a set of all Y and Y, so we're in f of U, so it's all the Y's in U, where there exists an X in, sorry, f of, yep. F of U is the set of all Y and Y, where there exists an X in U such that Y equals f of X. So if we are picking an element, my pointer thing doesn't work and that's so annoying because I need to be pointing at things and this is not helpful for people on the, for half of your classmates who are not here today. So we're picking this element in f of U, and if you look at that definition again, which isn't here now, but being in the image of a set U means that it's the collection of all of the places where the darts landed, right? So there is a dart that landed there. Does that make sense? Yes? And that dart's home is the set U. Remember, I have the set A in my hand, it's all the darts in my hand, I'm gonna toss them at the dartboard. Wherever they land, that collection of places where they land, that's f of A. Right? So if I'm looking at a thing f of U is an element, right? I have this thing f of U, I have this place on the dartboard. That means that I can follow back and find a dart that landed there, yeah? And so that dart's sitting in a set U. We tracking? Okay, so this dart U exists where f of X actually equals Y. We're okay? Yes, no, perhaps. Yeah, you're right. We don't have a function defined yet. I did try to do this. So we have this function f that's going from a set X to a set Y.
Oh, that's when you added the X and Y.
Yes. And we already know this function exists because we're looking at f of U, so we have this function f. And then the way that the image is defined is that under this function, right, there is a dart that landed over there. So f of that dart is Y, the target spot. Oh. Okay, so. So you have this X in U where under that function, it lands on Y. X is in U. We're trying to get that f of X or Y is an f of V. No or yes? We're trying to show that this thing is a subset of this thing. So we picked an element that was in here. We're trying to show this Y is in here. Yep. Y is f of X. Yep. Okay. X is sitting inside of U. Mm-hmm. Good.
Yeah.
U is a subset of V. Good. That's a given. We got to assume that. They told us to. Yeah. I'm gonna start writing the proof because maybe words around this will help and then we'll be less confused. And then I'll do more scratch work. We'll break and do some scratch work. Can we just use X and Y instead of talking about an A at all? Is that fine?
Yeah.
Cool. So we're gonna let f from X to Y be a function. And suppose U and V are subsets of X with U being contained in V. I didn't like the way it was, like my handwriting. I was just fixing it. Okay, so we have f from x to y as a function, and we're supposing that u and v are subsets of this set x, and u is contained inside of v. So again, our main objective here is to show that f of u is a subset of f of v. So we're gonna let x be an element, y be an element in f of u. Now, if you go back to the top of the page where your definition of that image, f of a is the set of all y and y, such that there exists an x and a, where y equals f of x. So for us on our problem, we're looking at f of u, whoa. It's gonna be the set of all y and y, where there exists an x in u, where y equals f of x. Is that okay with you or not okay with you? Okay, so that's just the definition of an element being in the image of a set. Means that there is something that got mapped to it, a dart that got mapped to it. Okay, so we have this element x in u where f of x equals y. All right, so that means since u is contained in v, y, which is equal to f of x, is an element in f of v. Yeah. Yep. I don't like the way that that is written. I'm gonna back up. Sorry. Since u is contained in v, x is in v, and therefore, and we have f of x is an element in f of v. But remember, y is equal to f of x, so we have y is an element in f of v, which is the thing that we were trying to show. Okay, so the first two lines are just the assumptions that we get to make from this statement. That next line is the beginning that let y be an element of f of u. That's just starting a subset proof that f of u is a subset of f of v. So what we're gonna do from this point, we have this element in the set on the left. We're gonna try to show that that element is in the set on the right. That's f of v. We're gonna use whatever this is in its definition. So y being an element in f of u means that there is an element in u that got mapped to y. So there's some x in u where f of x equals y. Now u is contained in v. So since x is in u, x is in v. And then you can apply the function again. Its image stuff means that f of x is an element in f of v. the y is f of x, so y is an element in f of v, and that's the thing that we were trying to, we started with it in the set on the left, we want to show it's in the set on the right. We did that, so we get the subset thing. Yes, no, maybe,
So. With like. So since U is in V, if we did the same, like. Applying F, it is just the same exact thing, just.
with the whole set, an element versus the whole set, yeah.
Okay.
Yeah, so, it works, basically what we're showing here is that that mapping is preserved on an elemental level, but it also is on a set level. So this collection of things, when it's mapped, is gonna stay, if it's inside of another thing, it's gonna stay inside of the collection of that other stuff. So you're taking this one element. Yeah, I don't know if I'm actually answering your question, so I'm gonna stop, but, did that help? No.
Let me rephrase my question.
Okay.
So like, U, that's a set.
Yep,
The F of U is,
also a set.
yes, it's a set, but it's the original set, but changed.
It's the original set, the collection of things that this set mapped to. It's the spots
Yeah.
on the dartboard.
Yeah,
Uh-huh.
it's after the.
After the function. Uh-huh. Yep.
Okay, so, okay. That's why they're basically just the same thing. That's why U or F of U is still inside F of V.
Yeah, there's a preservation that happens there, yeah.
Okay.
Yep. If they're subsets in the domain, then their images will be subsets in the range, yeah. Which is a pretty strong thing. As far as functions go, that's a pretty a substantial result. It doesn't feel like it, but if you've got these subsets over here and you put a mapping on them and they stay subsets under that mapping, that's pretty good. Okay. So what we're gonna do right now is take a break from proofwriting, and we're gonna answer these questions. We're gonna determine if these are functions, and if they're not, we're gonna talk about why. So we have this function from R to R given by f of x equals 1 over x.
Yeah.
The answer is no, but why? Because 0 is not in the domain of that function, yeah? Or shouldn't be.
Okay.
And the way that you write that using your set operations is that it's the real numbers tossed the set containing 0.
So now we change the domain.
Codomain's fine.
It's fine, being
Mhm. The range is not all real numbers. I guess the range actually is all real numbers. But the codomain is just the type of numbers that we're mapping into. Right, so it's okay that it's bigger than it needs to be. Is it bigger than it needs to be? You can get all real numbers that way. No, you cannot. Yeah, you can. Right? There's nothing you can't get. 0, you can't get 0. But we don't, right. So this one wouldn't be on 2, and we'll talk about that later, but we don't have to, the codomain, it's not important that it's the full thing. It's just like getting the type of number right. The domain it matters, right? The domain is the things that are actually, that you can actually plug in. So number 2 is also not a function. Yeah, and again, it's because of the domain. Or, and this may be, Logan, more kind of what you might have been asking, is that if you don't, it's been to know, the domain should be anything non-negative, so 0 to infinity, or you can call that R plus, R non-neg, my bad. The domain could be that, or you could change the codomain to be reals and imaginaries. I have no idea how to write the imaginary numbers, so we're just gonna write imaginaries. Okay, and then number 3, we have this set, this function f from R to R given by f of x equals plus or minus the square root of x squared plus 1.
What's a function?
It's not a function. No. This is not a function for the same reason that squared, that like x equals y squared is not a function. Because when you take a square root and you pick up a plus or minus, you are introducing 2 output values for 1 input value, and a function is 1, right? Every input has exactly 1 output. Right. Here, that's 2, right? Right? So the first 2 were tricks. Well, were thinkers. The third one was a trick because you were looking for the same thing, right? That's what's wrong with the other 2. That's not the problem anymore. Yeah. So sorry, none of those are functions.
What's the second, so the second one that says, or change codomain to.
Reals
number?
union the imaginary numbers.
Okay.
What are you writing?
I am thinking, I'm listening.
Oh, I guess
and
that's
then
fine.
I can't.
Yeah, whatever. That's good, good. Okay, find the domain and range of the following functions. The function that assigns each non-negative integer to its last digit. The domain is easy on this one. Help me out here. What's non-negative integers? You can call that z greater than or equal to 0, or you can do z plus union with 0. Or your textbook lovingly calls this z non-neg. That's a greater than or equal to 0 up in the exponent. Okay, on that first one. Cool. Okay, that's your domain. Each non-negative integer. Okay, it's assigning it to its last digit. So our range is the collection of last digits. Which is just 0 to 9, right? The last digit of a number is no? Yes? Yes. Don't understand what that even means. It's assigning it, so it's taking 587 and it maps it to 7. It's taking 693 and it's mapping it to 3. 7,084 and it's mapping it to 4. You get what I'm saying?
Oh.
Basically just like.
It's just a truncating, yeah, it's just,
computer just, you put in a number and
it's just
then
forgetting.
outputs the last.
Yep. That is what it is. And the collection of last digits that are possible are 0 through 9. Okay. A function that assigns each pair of positive integers to the first integer of the pair. This is again where your program just forgot some information, right? Or you're choosing for your program to forget what your user input. What's the domain? It's Rene Descartes. It's his plane. The Cartesian plane, Cartesian product is from Rene Descartes, mathematician. Okay. Well, have fun in history math. Z plus cross Z plus, the ordered pairs, X, Y. Taking an ordered pair and it's mapping it to just the first thing in the ordered pair, so just to X. So what is the range? Did you get out of class early again?
Yeah,
You want to do discrete today?
yes.
Cool. Talking about one-to-one and onto functions. You know what? I need to take a break. Do you want to just do it? No, okay, fine. All right, so your domain is Z cross Z. You're taking ordered pairs of positive integers and the output is the first integer in the pair. So the range is Z plus also. We're good? Yes.
Why would it be the Cartesian product?
Because it's just one thing. It's not an ordered pair answer. It's just the first thing. Taking 1, 2 and spitting back 1. Taking 7, 8, spitting back 7. 45, 13, 45.
Oh, it's just giving you the first number that you put, okay.
Logan this up.
What's that? What did you write, like to the right of 2 and like at the top, the X, Y, and what's that symbol?
It's an arrow?
What's the line at the beginning?
Yeah, this is a function arrow instead of an implication. Mhm. It's an arrow with a line.
Well, that's weird.
I've never seen that.
I've never
Yeah.
seen that in my life.
I don't know that that's an official symbol, is it?
I think so.
Okay, cool. We'll ask Alessandro.
I-
Phone a friend. Alessandro, is this legitimate?
Probably.
Okay, thank you for your help. Okay, so we've done a bunch of stuff with functions. We've talked about functions, talked about domains, ranges, codomains, images, pre-images, things of that nature. Now we're going to talk about one-to-one and onto functions, and we talked about that just a little bit. I hinted that this was coming. So you have this function f from x to y is one-to-one or injective if every y comes from one x. I'm gonna draw you some pictures. You ready?
It's helpful.
The arrow with a line in it is called a maplet. And it is
Oh my
used in
gosh.
mathematics and computer science to denote functions
A maplet.
or a maplet arrow.
I like it. Okay, so function means every input has exactly one output, so I shouldn't be drawing. Okay. We feel good about this? This is A, B, C, D maps into 1, 2, 3. Yeah? Yes?
Hmm.
This is a function. You're agreeing with me that this is a function. Every input has exactly one output. A didn't go to 2 different things. Yeah? Yeah, I haven't done the one-to-one thing yet. This is a function. Yeah, this is, yes. I'm using what you know to tack on a new thing. Okay, so this is just a function, right? Every input has exactly one output. This is not one-to-one because this output came from 2 different inputs.
Yeah.
One-to-one means when it is 1 to 1, one input for one output, right? So to make that one-to-one, we need more space over there. Over on the right. So we got A, B, C, D. Alessandro, my pointer thing does not work today. In Notability, the like,
Laser pen? Oh.
it's just not working. I click it and nothing happens. It's been happening all day. I brought it up to Mike and he was like, yeah, that just happens sometimes.
Oh,
What? That's just like a normal thing. I don't know. It's never happened to me till today. So to make this one-to-one, we need every input to go to one output. That's the function part, and every output to have come from one input. That's the one-to-one part. Good.
Did you show them potatoes in this class?
I have shown them potatoes. I'm getting to the darts. We've been talking about darts. We're gonna keep talking about dartboards. But my potato diagrams look like this, y'all. There's just y'all have seen them. Okay, so, but my professor in college called them potato diagrams. It's pretty good. So a function f from x to y is 1 to 1 or injective. If every y comes from 1x. So what that means is that if you have two things in the codomain that are equal. So you have f of a equals f of b. What that means is that they came from the same element, that a actually equals b. Or if you're really you like a contrapositive better, if your two things are different in the domain, then where they land in the codomain is also different. So I like to think about darts with this, that if you're looking at your dartboard, right? And you have two darts that are in the same spot.
Like the mirror there.
Yeah,
Up the arrow.
yes. It was the same arrow. But in this, it's not good. Right, so if you have two darts that actually landed in the same spot, they're not actually two different darts, they're the same darts. You just need to squint to see them better, right? So the idea is that if you have two different darts, they're gonna land in two different spots. If you have two darts that landed in the same spot, they're actually the same one dart. Yeah?
Makes sense. It's like a weird idea.
Yeah, true. That's fair. So
I'm not understanding about the one is two equal one, then it's just. I'm not following.
okay, I'm gonna say it one more time, maybe differently. I'm not looking at you to make you understand it. I'm looking at you because I'm thinking about how to say it differently, okay? That's what's
Sorry.
happening in my brain.
Sorry.
I'll look somewhere else to make you feel less uncomfortable.
No, I just don't understand what you're saying. Sorry.
I am saying that if you are sitting in potato number 2, you're over here in potato number 2, and you have this spot that was the target of two different darts.
Okay,
Well, actually, they're the same dart.
they're just the same.
Mhm. They maybe look different, but they weren't different.
Is it kind of like when you say that a function is the same thing,
As what?
like when a function is equal to each other, that they basically are the same?
When or what are you,
So-
in what context? Give me I don't know if that's the same or not. If two functions are equal, then two functions are equal.
So like,
Yes.
let's just say that has sine x plus 5 and then sine x plus 2. Basically the same thing.
They're not.
They're the same thing.
They're not the same thing. Their derivatives are the same. Let me hold on till we get to these examples. Let me do some of this and then we'll do these examples and then hopefully it'll make sense. Symbolically, when we talk about this is for every a, b in our domain. So every a, b, and x, this is our domain. If f of a equals f of b, then a equals b. So if you think you're looking at two darts that are in the same spot on the dartboard, you're not actually looking at two darts. You're looking at one dart. And you guys talked about this in college algebra, in pre-calculus, you talked about this, to invert a function, for a function to be invertible when you're talking about it, then you need it to be 1 to 1. And what that means is that it passes the horizontal line test, right? you're looking at a function that passes the horizontal line test, when you try to invert it, it'll fail if it fails the horizontal line test, that's where I need to be. If it fails the horizontal line test, when you invert it, it's gonna fail the vertical line test, which means it's not a function. Right? Because now every input has, more than one output, or some inputs have more than one output. Yeah. So what we're trying to get to here is being able to talk about invertible functions, or functions that have inverses. And so this is an example. You're looking at f of x equals x squared. So is this 1-to-1? Would this pass the horizontal line test? The answer is no. And that's because there are certain outputs that get hit twice, right? And so when you flip it, that means there are certain inputs that are going to go to different things. To two different things. So if you look at this, you have f of x is equal to x squared. Right, so to prove this wrong, you would say, okay, can I find a counterexample, right? So the counterexample, you want to know where you have P and not Q. So where you can find two numbers where f of A equals f of B, but A does not equal B. What'd you say, Whitney? Oops, I heard what you said. See, I already wrote it down. Oops. Whitney, what did you say?
I said -2 and positive.
So f of A is 4, and so is f of B, but -2 doesn't equal +2. So this thing is not 1-to-1. How could you make it? Yeah, you're going to restrict the domain. If you make this all non-negatives or all non-positives, right, then you would then pass the horizontal line test, and so you'd be okay, and would have a 1-to-1 function. All right, so we have now, you're looking at this set form, the set A, B, C, D being mapped to itself. So we have A, B, C, D. It's a pretty heavy sigh, Ruth. I don't have any idea what time it is. Okay. F of A goes to B. F of B goes to B. F of C, C goes to A, and D goes to D. Is this function 1-to-1? Does every input have one output that makes it a function? Does every output come from one input?
No.
Why not? Yeah. F of A is equal to F of B here. They're both B, but A doesn't equal B. So it's not 1-to-1. Hey guys, this is how I'm gonna write 1-to-1 when I'm writing it shorthand, but I'm never, ever, ever gonna write that in a proof for me, because I'm picky, and I'm gonna make you write 1-to-1 or injective,
If you can remember.
if you can remember which one is which. Okay. Do you have questions about number 2? Ruth, does that make more sense? Yes.
So when you're saying like the two darts are 1, that's what the f of A equals f of B equals B?
Yep.
That's what that is?
Yep, 2 darts were in the same spot at B. Were they the same dart? If not 1-to-1. If yeah, then it's 1-to-1. Yeah. But because they came from 2 different darts, A and B, then it doesn't work, like Merida and her mom. Whose arrow does she go in between? I need to watch the
Probably
movie.
guys that are fighting
The suitors, yeah,
Oh,
for the hand in marriage.
and,
Oh.
and they all like did archery, and then she was all like, I'm a better archer than you, and then she
Yeah,
ripped her
I-
dress, and then,
Because it was too tight.
I
yeah.
see, I see. I only watched the movie one time and I thought it was so weird and I never watched it again. Like, why is everyone bears? That's that movie, right?
Yeah.
Yeah, okay, yep, all right, sorry, spoiler alert.
It was one of my favorite movies.
Maybe I need to watch it again.
It's one.
Okay, I'll watch it again for you, Whitney.
That's just like how clear it is.
Well, yeah, right. Scottish, yes? No? Yes. Okay, so we have this function on number 3 from R cross R to R given by f of x, y is x minus y. Is this 1 to 1? I like that you just went with yes. Are you assuming that I'm not going to put you in a trap again? This is also not 1 to 1, but why?
I haven't had much experience with, multi-variables yet, so.
So why
I
were
have
you
no
so
idea.
eager to answer?
I have no idea.
I don't know. Yes.
50-50 shot.
You're right. You're right. So pick a number, any number, pick a real number. 7.
Okay, yeah.
Real number that's preferably not 0.
Right. Can you find 2 numbers that subtract to give me 7? Whitney, what 2 did you choose? Okay. Sky, what did you choose? Ruth, what 2 numbers subtract to give me 7? I panicked. Oh no. Okay, so these both landed on 7 on the dartboard. Are they the same dart? No. No, they're not. One lists 10-3 and one is 11-4. Those are not the same. They identify as the same once they get to the dartboard, but over here in this potato, yeah,
I think
I thought that.
no. Remember, this is that F, okay. F of 10-3 is equal to F of 11-4, right? They identify as the same under the function, but did they start out as the same? No. 10-3 is very obviously not equal to 11-4. Yeah,
I'm kind of thinking of another example, another way to explain it. Maybe it would be like hotel rooms. And so you're checking into a hotel room.
Mhm.
But like you can check in under a few names. You can check in under your first name or your last name or something like that. And so if every person goes to one hotel room, then it's 1 to 1. But if 2 different people go to the same hotel room, maybe they're sharing the room, like then it's not 1 to 1.
yeah,
And so but they have different names and they're going to the same hotel room, not 1 to 1.
good.
But I can check in under Alessandro or I can check in under Russo. And then I'm still going to the same one.
You're still the same
I'm still
person,
the same person.
same dart. That's good. You said that we all go to one room. I thought you meant, I was like, that's not, no, let's not use that example, but you mean our individual rooms?
Yeah.
Yes, mhm, good. I like that. Ruth, does that help you? Okay.
I think numbers help.
I don't know, when we used these numbers and I asked you if they were the same, you said yes. So I'm not sure if that's true, but let's try with maybe fewer numbers and see if it's better. So based on the statement of being 1 to 1, remember that was for all A, B in our domain. If f of A equals f of B, then A equals B. That's not what I said there. Here we go. All right, so how would we approach a proof that a function is 1 to 1? Okay, don't give me all the details yet. But like big picture, that's how I would approach it with the details, Dr. Thomas. Yes, okay, just keep going with me. I'll interrupt you when I'm ready. You go ahead.
So let X be a set
Hmm.
and let A and B be elements of X.
Okay. What would you do next?
Therefore, if A exists.
What's the P part of this statement?
And the way this has to be.
All right, that's what you would assume next, yeah?
Yeah.
We're not gonna wanna. Yet.
Oh, no.
So you're gonna assume they landed in the same spot, and then you're gonna do some math magic, and you're gonna say, they're actually the same. It was the same dart, or it was actually just Alessandro calling himself Russo instead of Alessandro, or Sandro instead of Alessandro. It's real confusing.
Oh.
It's just Alessandro
makes-
masquerading as Sandro, but he's
I
still
think
himself.
I think that makes a little
Different
bit more
name, same
sense.
person,
I think that makes a little bit more
different
sense.
letter, same,
Thing.
same thing.
A first name, B last name. Okay, so when you are gonna do this, you're gonna let you're gonna do that same thing. I'm just writing down these things in these blanks now. Let A and B be an X or your domain. You're gonna suppose or assume that f of A equals f of B. And you're gonna show, well, in fact, that's actually just both Alessandro going to his own room. Good, all right. So we're gonna do a proof now.
Oh. Okay.
That was not straight. Thanks, Notability. All right. So what do we get to do? We want to prove this function, f of x equals 5x minus 2 is 1 to 1. This is going to help you, Ruth. It's not just abstract anymore. We have an actual function to work with. What do we do?
We need to pick an A and B that's in that
That's in what?
the function.
That doesn't make any sense.
That's
The function's not a thing. It's an action, right? On a thing. What thing? The domain. Yeah.
Oh,
All right. So we are going to let A and B be in the real numbers, right? Because that's our domain. Good? Yeah? Okay. What do we assume? Okay. What does that mean in actuality here on our problem? But that's it. Yeah? Okay.
oh, really?
Yep. It's that easy. In theory. All right, so we're gonna let f from R to R be a function defined by f of x equals 5x minus 2. A and B, B and R, and assume f of A equals f of B. You're gonna say something like this. I'll wait till you're ready. It's the big reveal.
I'm excited.
I would like to ask you why you write so slow.
Well, I also have to slow down because my brain thinks so fast. I could have literally easily written all that, but my hand just doesn't write very fast.
That's what I just asked, is why you write so
No
slow.
idea. My brain thinks so much faster than my hand.
Oh,
I
that's,
don't think your hand thinks. That might be
No.
the issue.
that might be it, if you're waiting for your hand to start thinking. Oh, gosh, since A equals B whenever f of A equals f of B, since we discovered they're the same Dart or the same Alessandro, whenever they ended up in the same room or in the same spot on the dartboard, then f is 1 to 1.
Oh, nice.
So big reaction. Thank you. I didn't write down what I wanted to show, sorry, I'll add that now. We wanted to show that A equals B. Good? Okay, who's gonna take the lead on this next one? Yeah, sure, it's fine. What? What's wrong? If you start just here, it is. With a what?
X plus 3, you move it over. No, yeah, never mind. No. Yeah, I'll believe it.
X plus 3 squared. Plus 12. It's moving that way, so when you cut it off at 0, it's still just, it's less than half of a U. Yeah. If you move the other way, it would not work, you're right. Okay. I don't know why it got so big. It's just all imaginary, but it needed to be. If this was 3, 12's gotta be, okay. So, Whitney, you going? Is that what you wanted to do? Okay,
Scratch mark,
sure.
let A and B be elements of would be positive numbers.
They're not integers here, they're real numbers.
Mm,
So just, yeah. You can call that R plus if you wish.
Assume A equals FB. A plus 3 squared plus 12 equals B plus 3 squared plus 12.
But A and B are non-negative or actually positive, so we don't care about the minus. Yeah. Cool. Finally, yeah,
I want to show A equals B.
yeah, wow. How dare you forget that? Very important thing there. That's the same thing we're trying to prove all the time on a 1-to-1 proof. That's always what you want to show.
Okay, let the function, or let F.
This is H. So go on.
Produce, I'm just throwing an H there.
Just to throw you off.
That's right. I had you in mind when I used these notes of Dr. Dawson's.
From 0 to infinity, arrow, real number.
Good. H defined from 0 to infinity to the real numbers. Be a function. Good. Good, good.
Define I,
Hmm.
x plus 3 squared plus A and B be positive real numbers. So F of A equals,
This is still H.
you wrote F on the left, so,
Where? Oh, you're right.
then
Math. Arithmetic.
Maths.
Maths. Mm. Okay, so since A and B are positive real numbers, we have A plus 3 equals B plus 3, and finally that A equals B. Since A equals B whenever H of A was H of B, we have that, oh, my hand hurts. H is 1, 2, 1.
That's the best. She's fighting through pain.
I like how I decided I was gonna give myself room for the page break, but then didn't, just decided to write over the page break line there. Good, cool.
I mean, we can just like squeeze it in there, right?
Yeah, actually, that's a good idea. Let's.
Right between the 5. There we go.
Okay, how do you guys feel about this so far?
Well, okay, so why is there a plus and minus on the A plus 3?
I wasn't listening to you, sorry.
No, you're fine.
Square root, you take a square root, you got it.
What now?
Well, to get that square out of there, you're taking the square root.
Of both sides?
Yep.
And why isn't it on the B plus 3?
It's on both, it really doesn't matter, does it? It's on both, right? So if it's on the left, you can just move it to the right. Right? If they're both negative, it's positive anyway.
Yeah.
Right? If one of them's negative, just divide the negative to the other side, it doesn't matter. It's like a plus C when you do an integral and it eats all the other C's. No, are you doing plus C's in calculus? Is that, when do you do this? When do you do, you ever do that in Cal 1, right?
Yeah.
So, and if it's like a thing where you've split it into a bunch of different integrals, right? And they each have a plus C, you call them like C1, C2, whatever, but then at the end, it's just plus a big
Plus
C, right? This is a plus or minus that eats the other plus minus. I'm not sure why that's the example that I came up with, but you know, whatever, it's fine,
That plus or minuses taste good.
maybe. I am hungry, so that could be it. I'm hungry.
Oh, I didn't even recognize you. She said that it was eating the food.
We have time to do the scratch work for this one, but not a real proof, so. Logan, I'm putting you in charge. And
So. Let's do the A and B. Integers.
mhm.
So. When they equal each other.
Under the function, yep. Mhm. They identify as the same. Good.
So. You just have 18 equals.
B. Mhm, mhm, mhm. Okay. Good. That's it.
Where's the rest of this class?
It's a great question, Alessandra. I don't know. I'm assuming she's playing tennis. She's sick. No idea. No idea. It was half class till Kaylee got here. It was more than half class till Kaylee got here. She got here like 30 minutes late, so.
Oh. Yeah.
Hey, it's fine, right? This is a safe place. I don't know why she was late, but I'm glad she made it.
I didn't see Dan, we had that. This morning, I didn't see him there, so.
You had a map quiz?
Yeah, and that's it.
Oh, fun. He wasn't there either. Oh, no, it's not good. You guys have to turn in your homework before you leave, before I leave campus tomorrow at 1:20. I'll be here later than that because aftermath is happening.
You gonna do that? I have to go get ready for an interview.
You're gonna turn in your homework, right, Ruth? Okay, oh, good talk.
I was planning on it, I just haven't gotten there yet.
This is like talking with my children, like, I am speaking, you hear me speaking, no, yes,
I
no.
plan on it, I just
Okay.
haven't gotten